Hey everyone, and welcome. Today we are diving into a LeetCode problem that has that dreaded hard label, binary tree maximum path sum. But you know what? Don't even worry about that label. We're going to break this thing down piece by piece, and by the end you'll see it's way more intuitive than it looks. Let's get right into it.
Okay, before we even touch any code or data structures, let's just think about this like a puzzle. Imagine this tree is some kind of network, maybe a map of cities, and each number is the treasure you get for visiting. The question is really simple. What's the single most profitable continuous route you can take? That's it. That's the whole game we're playing here.
All right, first things first. Like with any good game, we have to know the rules. Because honestly, understanding the definitions and the constraints, that's half the battle right there. So what exactly do they mean by a path?
So the definition of a path seems pretty straightforward, right? It's just a sequence of connected nodes, and you can't visit the same node twice. But here's the kicker. The most important rule, the one that makes this whole problem interesting, is right at the end. The path does not need to pass through the root. That one little detail changes everything, and we're about to see exactly why. Let's start with a really simple example, just to warm up. In this tree, the best route is pretty obvious. You can see it right there. We just go from 2 up to the root at 1 and back down to 3. Add them up. 2 plus 1 plus 3, that gives us 6. Simple enough, right? Okay, but now take a look at this tree. The root is a -10, which we'd probably rather avoid. And if you look closely, the most valuable path is actually hiding entirely within the right side of the tree. It's that path from 15 through 20 to 7, which adds up to a whopping 42. And that right there perfectly shows the real challenge. The absolute best path might be buried deep inside the tree, completely ignoring the root. So that flexibility, the fact that the path can be anywhere, is exactly what makes this problem so tricky. It creates this kind of hidden conflict, a dilemma for every single node in the tree. Let's unpack what that conflict actually is. So as our algorithm travels through the tree, every single node has to ask itself a fundamental question. It's like it has an identity crisis. It has to wonder, am I the top? Am I the peak of the best path found anywhere in this tree so far? Or am I just a stepping stone, a bridge, on a much longer, much better path that goes up through my parent? And here's the thing, it has to consider both possibilities. Now, you might be thinking, well, why can't each node just add up its own value plus the paths from both of its kids and pass that total up? And that's a great thought, but here's the problem. A path has to be a single continuous line. If a node tried to pass up info from both its left and right children, it would be handing its parent this Y shape, and the parent can't connect to that. It's not a valid path. A node can only offer one single branch up to its parent. And that very constraint, that problem of the Y shape, leads us directly to the solution. This is the big aha moment for this problem. The whole trick is to realize that each node needs to calculate two completely different values. This is the core insight that unlocks everything. Okay, here's the big idea right here. Every node has two jobs. Job number 1, on the left, it considers itself as the potential peak of the entire best path. Think of it like a V-shaped path, with that node at the very bottom of the V. It calculates its value plus the best paths coming from its left and right children. It then checks if this V is the best we've seen so far in the whole tree. Job number 2, on the right, it figures out what it can pass up to its parent. And remember, this has to be a straight, continuous path. So it takes its own value and adds the path from only its strongest child, either the left or the right. That's the value it returns. And there's one more super clever trick. What happens if the best path a child can offer is actually a negative number? Well, we just ignore it. We treat it as 0. Why? It's simple, really. We can always just choose to start a brand new path right here at the current node instead of continuing a path that's just going to drag our total sum down. It's a beautifully simple optimization. All right, the theory is cool, but let's see this thing in action. We're going to roll up our sleeves and trace our two-value logic all the way through that second, more complicated example. Let's see how it works. So we're going to solve this using a method called depth first search, or DFS. And don't let the name scare you. All it really means is that we're going to travel all the way down to the deepest leaves of the tree first. Then, as we start climbing back up, each node is going to do those two jobs we just talked about. First, check its V-shaped path and update our global answer if it's a new record. Second, return its best straight path value up to its parent. Okay, so here's our tree again. We're going to have a global variable, let's call it ants, to keep track of the best path sum we've found so far. We'll start it off at something super low, like negative infinity, so that the very first path we find is guaranteed to be bigger. Now, the recursion begins, diving all the way down.
Let's just fast forward to the most interesting part, the moment our code is processing node 20. At this point, it's already visited its children. The node 15 has returned a value of 15, and node 7 has returned a 7. So now node 20 does its two jobs. Job 1, check for a new global max. It calculates that V-shaped path, its own value, 20, plus 15 from the left and 7 from the right. The total is 42. Boom, that's a new record, so our global ANS variable is updated to 42. Now, job 2, what does it report back to its parent? It has to be a straight path, so it takes its own value, 20, and adds the larger of its two children, which is 15. It returns a total of 35 upstairs. And finally, we're back at the root, node -10. It's received a 9 from its left child, and that 35 we just calculated from its right child. So it does its first job. Is the path through me even better? Let's see, -10 plus 9 plus 35, that's only 34. Well, 34 is not bigger than our current record of 42, so the global ANS stays exactly where it is. The process is now finished, and we have our final answer.
And there you have it, 42. The algorithm worked perfectly. It correctly found that the path 15 through 20 to 7 was the richest route, even though it was totally separate from the root of the tree. So we solved it, which is awesome. But what's the big lesson here? What's the core idea you should really hang on to? Because this isn't just about this one problem. It's about a really powerful pattern that you'll see over and over again in tree problems. The absolute key is this dual role pattern. In so many recursive tree problems, you'll find that a node needs to do two different things. First, it does something for the global good of the whole tree, like checking if the best answer runs through it. But second, it returns a totally different local value that only its immediate parent needs for its own calculations. Getting your head around this global update versus local return pattern is a total game changer. And of course, never forget that little max of 0 trick for chopping off paths that are just dead. And that brings me to a final question for you. This pattern is everywhere. A classic example is the problem diameter of a binary tree. So my challenge to you is to think about that one. How does that problem also force a node to calculate one thing for a global answer, the diameter, while returning something totally different, its local depth, to its parent? Give it some thought. Thanks for joining this explain.